All right, guys, welcome everyone. So today we are very happy actually to have Varun here to give us a talk. So Varun right now is actually a postdoc in Microsoft Research in the Adaptive System and the Interaction Group. And he will also join UIUC as a professor in 2023. Varun got his PhD from UW Medicine, and he actually also a long-term collaborator with people like Nicholas Papernaud from University of Toronto. So Varun has done actually many interesting work in the domain of trustworthy AI, and he is also a rising star in this field. So without further ado, so Varun, the floor is yours. Please go ahead.
Thanks, Yang, I guess, for the very kind introduction. It's good to hear that I'm a rising star. All right, so thanks everybody for taking time to kind of listen to me talk about how I think we should kind of approach problems in this trustworthy machine learning space by looking at it through the lens of different areas of computer science. So the title of my talk is how interdisciplinary research yields new insights. And I'm going to be specifically talking about how this is true in the context of like trustworthy machine learning, right? And I guess specifically private machine learning, right? So, all right. So why is private learning important, right? So and learning, I guess, is this paradigm that I'm defining where there is some data and we're using this data to train a model, and this data is obtained from a set of users. Well, sometimes this data may have sensitive attributes, right? There are some things that you may just not want to share in the data, and this may be learned by the model. Or sometimes that the model you may learn on this data may leak something about the owner of this data, right? Both of which are like problems, and I'm hoping like to this audience we kind of understand why private learning is so essential, and the de facto solution to solving these problems, right, regarding sensitivity of data and attributes, is to train the model with differential privacy, right? Either perturb the gradients during training, or use output perturbation, or perturb the inputs, anything that you want to do. Right, but there are some main downsides to using this approach. Sorry, just going to move this. All right. So the first downside is it kind of empirically we see there's some trade-off between the privacy that you want to get and utility. So if you want very strong privacy guarantees, the model you learn often is not very utilitarian. So the accuracy is not that great. The guarantee of differential privacy itself sometimes is not like super easy to understand. So we don't understand what DP means, why is it giving privacy? How can I communicate these guarantees to like a layperson, for example? So I guess I'm in Microsoft right now, and one of the big challenges is you want to ensure privacy of customer data. And we have like large engineering teams that are kind of helping with these efforts, but we have to somehow convince the engineers that this is the right thing to do, and also communicate to the legal team what like epsilon of 2 means in the context of privacy. Right. And there's another challenge, which is, we have trained these models with differential privacy, and it allegedly preserves privacy. But how can we actually audit that this is happening, right? It's not very easy to kind of audit these mechanisms that involve privacy post hoc, right? And this is not just true for differential privacy, but other things like data deletion, right? Like, so if I want my data to be deleted from a trained model because I don't trust the model provider, I can't really verify this happened post hoc. So these auditing mechanisms are not very clear, right? So in this talk, I'm going to be discussing how we can borrow insights from different research areas in computer science to alleviate some of these concerns that we saw earlier. And specifically, I'm going to go through 4 case studies, right? First, we're going to discuss how we can create like more utilitarian synthetic data with strong privacy guarantees, right? Then I'm going to be talking about like some new ways of performing membership inference that are a little bit more intuitive, and hopefully we understand why it works, right? I'm going to talk about scenarios where users want to delete their data from trained machine learning models with some strong guarantees that this operation has actually happened. And finally, I'm also going to be talking about some new class of applications, like how we can enable more private authentication mechanisms, right? Like things like Face ID, but a little bit more private. And for all of these case studies, the key insight doesn't really come from, I guess, machine learning or trustworthy machine learning, but it comes from like different areas of computer science, right? Like, so we have causality that is helping, and algorithmic stability in the other case, and like a bunch of cryptographic constructs that help the last 2 use cases. And we see that if we're using insight from these different areas, we have very strong advantages. right? So the first case, I will tell you how causality helps create more utilitarian synthetic private data. So there's like a better privacy utility trade-off than just using privacy for learning without any causality. In the second case, we'll discuss how this notion of label memorization helps kind of understand when membership inference may happen. In the third case, construction of cryptography like verified computation help users get strong guarantees of specific computations being performed. And in the last case, fuzzy extractor is another cryptographic construct that helps like remove some strong assumptions that we need to run applications today, like reliance on trusted hardware, for example. Right. So let's kind of just jump into the whole process. So what is synthetic data creation, right? Synthetic data creation is this process where I have like a particular database, and it has some attributes that I'm not really comfortable sharing directly. So I feed this database to some tool chest that creates synthetic data. It runs some algorithms. It can be anything. It can be like give the guarantees of key anonymity or whatever, and the output is going to be some synthetic database which ideally does not have these same attributes that I wanted to preserve, right? So what do we actually want from this tool chest, right? So this tool chest should work for like arbitrary data set sizes with arbitrary dimensionality. It should result in a synthetic database that preserves the statistical qualities of the input, right? I don't want my synthetic database to contain completely random data compared to what is in the input database. And finally, you want to create synthetic database, synthetic database in a fast way, right? So you don't want this tool chest to be very, very slow, right? And most important of all, with the hope is, that the synthetic database is somehow private, right? It does not leak any information about you that is contained in this input database, right? So I didn't really say what we can do in this tool chest, but if we naively do it, right, you're susceptible to these linkage attacks. So even if you somehow obscure some particular attributes in your synthetic data set, you can somehow connect it back to the original data set through some side channel information. I guess there's some seminal work by Narayanan and Shmartikov that kind of explains how this can be done. So they de-anonymize, I think it was the Netflix data set in 2008, and this was all the rage back then. And the primary shortcoming, I think maybe up like a year or two ago, was that we were not able to kind of scale to databases of a large dimensionality, right? So like, how do we actually mitigate these issues? Well, to like, I guess, alleviate these linkage attacks, you train your toolkit with differential privacy. You somehow augment this toolkit with some mechanism to provide differential privacy, and these linkage attacks somehow go away, right? But differential privacy comes with all of these other problems we saw earlier, which is there's a privacy utility trade-off and so on and so forth. And to circumvent the scalability problem, we fall back to like using generative models like GANs or VAEs or autoencoders. That now we have like these cool class of models like transformers and diffusion models and so on and so forth, right? But like I said, if you're using a generative model with differential privacy, there's this privacy utility trade-off that we have to deal with. So how do we actually mitigate this? And that's the remaining portion of this segment. And in this work, we basically fall back on using causal learning to give us some stronger trade-offs. And let me just give you a brief primer on what I mean by causal learning. So there is some particular database, right? And I use some causal discovery algorithm, something like no tiers by Zhang et al. And the output is some causal graph, right? And a causal graph is just indicating causal connections between the different attributes in the database. So concretely, what I mean is, let's say this database is what we're seeing at the bottom of our screen. There's an attribute called diet, there's something called age, and then there's something called weight. I guess this is not representative of anything real. It's just something that I made up yesterday. But it kind of makes sense, right? If you eat a lot of unhealthy food, for example, you can become very obese. And if you eat not so unhealthy food, and I guess you're relatively younger, your body mass is not really high. So like intuitively, the causal relationships that we can see is what you eat somehow influences your weight. So there's some connection between diet and weight. And there is also some connection between your age and weight. So younger people weigh lesser than potentially older people, right? So if I run a causal learning algorithm on the database that you're seeing on the left, the causal graph is what we see on the right, right? Great. Awesome. Any questions so far? Okay, great. Awesome. So how does causality fit into this whole equation of creating synthetic data that is more private and utilitarian? So in the status quo, what I have is some input database, and I feed it to some generative model that's going to be trained with DP, and the output is going to be some synthetic database. And my claim is the synthetic database is not going to be very utilitarian, meaning the data is not going to be super good, right? What I'm going to do now is I'm going to run some causal discovery method on this input database, and I'm going to get a causal graph, right? And I'm going to feed this causal graph as some side channel information to my generative model, right? So what does this exactly mean? So in the context of VAEs, for example, I'm going to change the architecture to preserve these causal relationships in the VAE, right? And this is like a very laborious process, and I guess this is a shortcoming that we'll kind of discuss. But let's assume that we can do this. I'm providing this causal information as some architectural specification for this DP training model. And we have like a lot of theoretical analysis in the causal literature, which basically said that these models that are enhanced by causality are more stable from an algorithmic stability perspective. And what this means is that naturally the privacy guarantees that we get from these stable models are stronger, right? So there's a world where I don't have any causal side channel information, which I'm giving to a generative model. And there's a world with this causal side channel information I'm giving to the generative model. The stability of the model with causal side channel information is higher, right? And consequently, so is its privacy, right? Another way of kind of just visualizing this is if I fix a particular privacy budget, the causal model is always going to give me more utilitarian data, right? And I'm happy to go over the details of, like I guess the derivation, but I guess we have a paper with more details, and I can share details if you want to look it up. And we have some theoretical guarantees that this is actually true, right? So what does this actually practically mean, right? Let's say I'm going to train some classifier on the data that I'm going to get from these generative models. But the generative models themselves, I'm going to train in 3 different ways. The first approach, I'm going to train it with standard DPSGD. The second approach, I'm going to train it with the DPSGD plus some causal side channel information. And the third approach, I'm going to use some technique called DPPGM, which is one of the state-of-the-art approaches for creating synthetic data in 2021, right? And here are the results, right? So we can see that if I'm training the model with just DPSGD, the data that I'm going to get is the least utilitarian. That's the blue line, right? DPPGM, which is one of the SOTA approaches, gives you significantly better utility than just DPSGD, right? But if we provide this causal side channel information for the same privacy budgets, the utility of the models that are being learned are significantly higher, right? And this is like for 2 data sets related to predicting whether students do well in certain classes or not. So it's called the ED data set, right? So we saw, I guess we briefly saw how causal information can somehow improve like the stability of algorithms, and this improves the privacy. But there are some interesting questions that can kind of emerge from this line of research, right? First, causality, basically this causal graph shows us connections between different attributes. So can we leverage these connections to kind of understand why membership inference happens? So are some attributes more susceptible to privacy attacks than others? I guess my colleague Shruti gave a talk a couple of seminars ago on connections between causality and membership inference. And they have a paper coming up in CCS this year that explores this topic. It's very, very interesting, right? Some of the main takeaways might even be that you might not even need differentially private learning to defend against membership inference, as long as your model is kind of causally stable, right? There's another challenge, which is in whatever we described so far, I have to perform like this 2-step process where I have to first discover this causal graph using some algorithm, and then manually encode this causal knowledge into my generative model by modifying the architecture, right? Can we simultaneously do both? So are there a class of models that perform causal discovery and generation simultaneously, right? Studying these are open questions that my colleagues in Microsoft Cambridge are looking at. So if any of you are interested in them, I can put you in touch with people in this area. And finally, can we understand how these foundation models, or Microsoft calls them platform models like GPT-3, for example, how private they are intrinsically? So for example, if we have some knowledge of how the data was used and how these data are connected to like these parameters that are being learned, can we somehow comment on the intrinsic privacy of these platform models? Because we have seen that training these large models with DPSGD, for example, is just like time-wise prohibitive and has like a strong detriment on accuracy. But if we fine tune these models at DPHGD, it actually works well. So can we explain this phenomenon a little bit better through causality? Right. But speaking of like a membership inference, right? Let me kind of again refresh the audience's mind on what I mean by membership inference. This part of the talk, I'm going to be talking about why membership inference works, or at least why we think it works in some cases. So what is, I guess, a privacy attack, right? Like, so there's a model that's trained on some private user data, and this model gives some sort of predictions at test time, right? There's some adversarial entity that interacts with these predictions, and the aim of this adversarial entity is to infer some sensitive information about the training data, or just find out what the training data is itself, just by observing these predictions of this trained model, right? So one particular example of performing membership inference is this approach by Nicholas Carlini and his colleagues, which appeared in Oakland last year, called LEADA, right? So there they assume that there's some data set, and the model is trained on this data set in one world. I'm going to call this model A. And in another world, there's model B that's trained on a data set without one particular record, right? And what they do is they run some very clever tests on both model A and model B and see how the behavior of this model somehow differs in the presence or absence of a particular point, right? So this behavior could be like how good this model is at predicting the label of that particular data point or some other statistics. And they combine this behavior with some hypothesis testing to give some very strong results on membership inference accuracy, right? There's this completely other line of research called label memorization, which basically wants to understand how good models memorize certain samples, right? And what they do is they train a model with a particular database, and they obtain a particular model, let's say model A, and they train another model on a database without a particular record, and they obtain some model B, and then they observe how these models A and B differ in predicting the label for sample XY, right? If you look at the previous slide and this slide, there's some great similarities, right? Here, label memorization is a very specific task, which is predicting the label, whereas membership inference involves predicting the label as well as some other things that are going on under the hood. And in both worlds, they run multiple randomized trials, train like a bunch of shadow models and do all of this stuff, right? So when we looked at both of these, the Carlini attack and whatever Vitaly Feldman proposed for label memorization, we thought, there's like an obvious connection, right, between memorization and membership inference. So to kind of unearth this connection, we ran like an experiment to see if there's some correlations between the two. So the primary aim is we created a data set with a mixture of two distributions, right? So you should visualize this as mixing an MNIST data set with some CFAR10 images, right? So there is an underrepresented population in this distribution. So in this case, it is maybe like, if I have a data set of 60,000 MNIST images, I'm adding like 100 CFAR images. So this is my underrepresented population. And the MNIST samples are my overrepresented population, right? And I have like this data set, and I run Carlini's attack on all samples of this data set. And I run Vitaly Feldman's algorithm for label memorization on all samples of this data set. And here are the results, right? So the red points are CFAR and the blue points are like MNIST, for example. So you can see that the CFAR samples in this mixture data set are very, very susceptible to memorization compared to the MNIST samples, right? And at the same time, the CFAR samples are also the ones that are more likely to be susceptible to membership inference, which is what we see on the y-axis, right? And we also see there's a strong correlation between being susceptible to memorization and being susceptible to membership inference. Well, it's not really strong, but it's pretty good, right? And if you actually want to visualize this, I'm just not making it up, these red points are what you're seeing on the right of the screen. The most memorized points actually belong to like a completely different data set. So it's not really CFAR, I guess this was SPHM. Okay. And all these, the blue points are what you're seeing on the left. Just I guess all of this stuff. Right. So intuitively, and I guess like, experimentally, we're seeing that there's some correlation between membership inference and memorization. So can we somehow leverage this knowledge to kind of design better membership inference attacks? I guess that was the question that we asked. And it turns out there's some way that you can. So I'm going to propose this new membership inference game that was kind of inspired by something that Saeed and Somesh did this year. And the approach is there's some interaction between some adversarial entity and a challenger. Okay. So the adversary has the capability to send the challenger two data sets. I'm going to call this D star and D. Then the challenger basically flips a coin at its end. And if the coin returns heads, for example, this challenger just copies data set D into its local copy. If it flips one, then it copies a fusion of both D and D star. Then the challenger performs training on this D prime data set and obtains a model, right? And it returns this model back to the adversary. And now the adversary's objective is to basically find out whether the challenger flipped heads or tails, right? So in some sense, the adversary basically wants to know what was used to train this model, right? And this is like the standard membership inference game. This adversary basically wins in this case if it is able to correctly predict whether the challenger flipped heads or tails, right? So we've seen this game multiple times in like different ways, like starting with the paper from Sam Yom, and I guess also in this paper by Said. So the question we ask is, what happens when this data set D star is filled with samples that are highly likely to be memorized? And in literature, these highly likely to be memorized samples are called singletons. So the question is, if this adversary gives this challenger a data set with samples that are going to be memorized with very high probability, can this adversary basically determine if those samples were used in the trained model? Right? So I'm going to show you some results of what happens when this actually is implemented. So we tried different membership attacks where the setting is the adversary returns, shares all these particular data sets to the challenger, right? And for the time being, just focus on the particular rows where we see singletons, right? So singletons are the ones that are highly likely to be memorized. And we see that if the data set comprises of singletons, the adversary's success in identifying these underrepresented samples, which is the column that's highlighted, is significantly higher when the data is compared to the data which is not singletons, which are the corresponding rows above. So for example, here you see the success is like 0.91 compared to 0.65. And this is true across all attacks. And this attack by Carlini at the bottom is like the strongest known membership inference attack. And here we can see that we can always successfully identify. So the AUROC is like 1, right? And this is true even in regimes where Carlini kind of advocates you want to measure the TPR at some low FPR value. So here, for example, we're always successful. It's like 100% in this box. And all these other attacks here, you may say it's like really bad, which is bad because these attacks are not designed for success in that particular regime, right? So these singletons are really, really powerful tools that privacy adversaries can exploit to identify membership, or rather perform effective membership inference. We can also see that in the underrepresented set, this privacy adversary is very successful in identifying this underrepresented set, right? Compared to identifying all samples. And this is true in both these regimes, whether we're fixing a very low FPR value or across, right? So the TLDR is basically that the samples that are highly likely to be memorized are also very, very highly susceptible to membership inference, and adversaries can very strongly exploit this fact. And there's a strong empirical evidence to suggest that this is true. Okay. So by studying this thing, several interesting open questions have emerged. I'm hoping the community will take action on this. Right. The first is we don't really have a very neat closed form solution for the concrete advantage a privacy adversary has in these settings. So empirically, we are seeing like the number is like 1. Theoretically, we want to show the same, right? In this setting where we're providing highly memorized samples, we want to say the adversary is always going to succeed, right? Determining memorization by itself is a very, very expensive process. right? Like, so as an academic institution, running these experiments is like super cumbersome. You have to train like thousands of shadow models on the same data set. And, if you're not at Google, for example, doing this is non-trivial, right? So can we design very effective tests for measuring memorization, right? And we also want to understand how DP works as a defense mechanism to those samples that are highly likely to be memorized. So if I train a model with DP, but still include samples that are highly likely to be memorized, is this adversary still successful? We don't know the answer to that question, right? So now I'm a user. I know that my data is very highly likely to be memorized for whatever reason, but I still want to preserve my privacy. What do I do? I have like this option of basically telling this model owner, hey, model owner, forget my data. So I'm assuming for the time being, we're in utopia. And this data owner can basically say, hey, model owner, delete my data. And this model owner is going to say, okay, right? And this problem, I guess, of machine learning is motivated by public policy and laws like the GDPR or CCPA. There are multiple ways this model owner may do this in this utopia. It may run some exact unlearning approach, right? It'll retrain the model without my particular data sample. Or it can use some approximate technique like what Chuan Gu and his colleagues at Facebook have done to estimate the influence of my data point and just remove it from the model parameters. This is like significantly cheaper to do, right? So in this ecosystem, I somehow assumed that this model owner is actually going to comply with my request all the time. But what if this model owner is malicious and basically says, hey, I'm going to tell Varun that I deleted his data, but how is he actually ever going to find out if I did or not? There are several cases why this model owner may be malicious in such a way. First, to run these approximate unlearning techniques that rely on influence estimation, like computing the influence for like these large class of models is expensive, and influence is not unique. And some of my colleagues in Toronto have shown this to be the case. And there could be like correlated data entries in the data set, which may exacerbate this problem. So even if you remove my data point, my brother's data point, for example, could be in the data set, and the model parameter might still be the same, right? Running these unlearning techniques may at times be computationally expensive, and it may also introduce some utility degradation, which the model owner obviously may not want, right? So like, how do we actually solve this problem where I'm requesting data deletion and this model owner is saying they're doing it? How can I verify that's true? So I'm going to fall back on this construct called verified computations, which has very strong ties to probabilistically checkable proofs. And there's a very nice CACM article by Michael Wolfish and Andrew Blumberg in 2015, for those who are interested. And verified computations is a very cool concept where there are two entities. There's a verifier and a prover. And this verifier basically wants to delegate some computation to this prover. So you can think of a setting where you want to run some computation on Azure, for example. And you get the result from Azure, but you want to verify that this result is correct and is the output of your computation. So this verifier basically gives the prover a computational task. This prover performs some computation, does this task, and also creates like some small proof that this task was indeed executed correctly, and returns this proof back to the verifier. Then this verifier on its side runs some verification mechanism and basically says, hey, the proof is correct. You've actually performed this computation that I'm requesting of you. So there are many ways of running verified computations, right? One of the techniques that one may use to achieve this particular abstraction can be through snarks. And in our particular case, the setting is if I replace this verifier with the data owner and this prover or the model owner, the ecosystem is still the same, except this data owner says, hey, perform this unlearning task for me. And this model owner has to do this unlearning and returns a proof of unlearning back to the data owner. Right? And this data owner can verify this proof and basically say, hey, this unlearning has happened or not. And we can achieve this by using cryptographic constructs called snarks, right? So they're succinct knowledges of computation being performed. So now, basically, I want something called a proof of unlearning. How do I actually achieve this? I can break down this unlearning problem into like two steps. The first is this model owner must basically delete some data, right? And it has to prove that this data was indeed deleted, right? So I'm deleting data from my training data set. So I have this updated training data set without my particular data. And then using this updated training data set, I want to perform training or whatever, unlearning. I'm going to call this model update, right? So it may run some computation task on this updated data set and obtain some new model, right? And this computation that I'm defining has to be some valid unlearning method. It can be retraining or anything, right? As long as it's tied to unlearning. And all parties that are participating in this protocol will kind of agree that this is the computation being performed ahead of time, right? We have like some very clever constructions to do all of these things very efficiently. I want to very briefly talk about how we support data deletion. We use these. We again use these cryptographic constructs called authenticated data structures that verify some operations very, very quickly. But very naively, you can think of it as two Merkle trees, right? There's one Merkle tree which is on the left, which contains all the data that you're using for training. We're going to call this HD. There's another Merkle tree that you use for the data that you're deleting. We're going to call this HU. And Merkle, I mean, for those who don't know, you can basically verify presence or absence of a point in a Merkle tree by just looking at the root of the Merkle tree. So it's just a tree with hashes of data points, right? So at some iteration I-1, this is how the state of the two Merkle trees is. At some later iteration, some user may say, hey, add 2 data points and remove these 3 data points. So the Merkle tree on the left is modified as so, these new data points are added to the right side of the Merkle tree, and the removed data points are added to the second Merkle tree, right? Okay. I'll explain why I guess we're using Merkle trees in the next slide. And I guess for the proof of model update, we just create a cryptographic circuit based on the unlearning method, and you can create a snark for this particular circuit. Cool. So like going back to the original problem, I want to delete some data. How do I actually do this in some verifiable way? There's first some setup procedure that is run between all participating parties so that you can set up your cryptographic primitives easily with some parameters. Then the data owner basically says, hey, model owner, delete the sample D. Under the hood, the model owner updates the training set to not include this particular sample, then obtains a new model performing some unlearning computation using this updated training data set, computes the proof for step 2, which is this new training data does not include sample D. Sorry, it computes. Yeah, sorry, there's a typo. Step 4 is it computes a proof for step 3, right? So I'm computing a proof that the model is obtained using this updated training data set. And like I said, we can do this with a snark. And then it'll also compute a proof that the training data does not include the sample D, right? And this can be made more efficient by the Merkle tree because I have 2 Merkle trees. And if my data point belongs to one Merkle tree, by construction, it cannot belong to another Merkle tree. And verifying this is very, very easy. You can just look at the roots and say, hey, this data point is in Merkle tree U, not Merkle tree D. So you don't even have to look at both. Right. So this model owner computes both these proofs and returns these proofs back to this data owner. And this data owner verifies the proof of update. So verification of a proof is very, very fast. I'll show you the next slide. And also verifies the proof of data deletion, which is looking at the roots of these Merkle trees. It's also very, very fast. There's like a lot more details, I guess, under the hood that I've kind of abstracted away. If you're interested, I guess there's a paper up on arXiv that I'll point you to. So does this actually work, right? Like there's a lot of mumbo jumbo. To actually evaluate this, so I guess for those in the audience that are unfamiliar, anything that involves cryptography is like in the status quo, like very, very slow. It takes a lot of time and computational resources. So we evaluated using these following data sets. So these are by no means like your MNIST and CFAR data sets. They're very small. But even with these data sets, I'll show you some numbers that may show why this research is kind of interesting in some way. So on the top half of the screen, you can basically see the time that takes to set up these cryptographic primitives, like creating the circuit for the snarks and so on and so forth. As we see the data set, as the data set size increase, and when I say size, I mean it's a product of the data points and features, because this somehow dictates the size of your circuit. We can see that the time required also increases linearly. And similarly, depending on the class of model you're training. So for example, linear regression versus like a simple 4-neuron neural network, the time required for the process increases linearly, right? It's like in the order of like 3 hours for something as simple as like a 4-neuron neural network on a data set with 128 points. And creating the proof, for example, can take somewhere close to 1.5 hours. But this proof can be verified in like under like 10 seconds. And then this owner basically has the guarantee that the data point was indeed removed, and the model that was trained without the data is indeed correct, based on the guarantees of these cryptographic constructs, right? So you don't even need to run like things like influence estimation, for example. Like by construction, this is correct. It's what the guarantees of cryptography give you. So we're studying this problem, I guess several open questions emerged. Like earlier I said, you can run any unlearning method, but this is not necessarily true. The unlearning methods have to be very strictly compatible with our definition of unlearning, which is the method must first delete the data and train a model on this updated data set. So it's unclear if all unlearning methods satisfy this definition. So designing unlearning methods that may be compatible with this cryptographic scheme gives strong guarantees of data deletion, interesting research. As we saw in like the previous slide, just creating the snark, for example, just takes 4 hours, right? So can we design smarter cryptographic primitives specifically for the context of data deletion in these stochastic optimization problems? There's extensive research being done on this in the cryptography community. It's like an interesting open problem. And there's a lot of redundant computation being done because there's only two parties, which is the data owner and the model owner. And there's a lot of redundant computation being performed. So can we offset some of this redundancy by assuming a trusted entity like a trusted auditor? So the nice thing with this cryptographic solution is even if the model owner, which is the one performing data deletion, is somehow malicious, they cannot convince the data owner that they performed unlearning without actually doing it. That's why cryptography is powerful here, right? Awesome. I guess like the last part of my talk I'm going to very quickly rush through is how like private ML can enable a new class of like applications like user authentication. And we're specifically going to be talking about biometric authentication. There's a user and they're defined by like a bunch of these biometric attributes, like their photographs, for example, or their iris scans or like their fingerprints. And once they provide this to some particular sensor, they're no longer behind like this wall to access a particular service, so they can interact with the service. So think of like you're trying to authenticate yourself to your phone. Your Face ID basically takes a scan of your face, and now the phone is unlocked, so you can interact with your phone and so forth. So the problem with authentication mechanisms like this are that you have like finitely many biometrics, like I don't know, you have like 10 fingerprints or something. So preserving the privacy and secrecy of these biometrics is super important, right? We don't really know what is going on under the hood for authentication, right? These authentication algorithms are like typically black box and not really audited in a secure manner. And finally, there's some strong reliance on trusted hardware. So what I mean by that is at the time of authentication, when I first get my iPhone, I calibrate Face ID, right? I take different photos of my face from like different angles, and all of these biometric readings are somehow stored on the phone in some allegedly trusted hardware. But there's a lot of research that shows this hardware is also susceptible to numerous attacks and leaks a lot of information through side channels, right? So this reliance on secure hardware is kind of problematic, right? So like for the first two challenges, somehow like machine learning helps, right? Like, so like how does machine learning particularly help? My facial image is somehow converted to some embedding by some neural network at the time of like enrollment, and at subsequent authentication, even if my face is somehow different, right? Like for example, if I add like glasses or something, this neural network may obtain some embedding, which is very similar. And if I feed these embeddings that are obtained during the enrollment phase and authentication phase through some cosine similarity function, it's going to say, hey, either this person is the same or not the same. So this is pretty much the approach that Apple uses for like Face ID. The problem still remains that these embeddings that are created are stored on secure hardware, right? If not the original face itself or like the original fingerprint itself, right? Like, so now the question is, can we actually get rid of this trusted hardware assumption? Right? And it turns out we can. There's another cryptographic construct called fuzzy extractors. For those who are interested, there's a paper by Juels and Wattenberg in CCS 1999. Yeah, it's pretty old. And fuzzy extractor is a very cool construct. It basically say that if there are two inputs, x and x prime, that are at bounded distance from each other, right? And distance can be any metric, right? If I feed these inputs to my fuzzy extractor, I should get the same secret key. So you can think of this as the following. If I have two images of my face, just in different conditions, as long as they are indeed me and they're not significantly different, I should be able to authenticate myself to the device, right? And this primary construct, the mechanism that is supporting all of this magic is error correcting codes. So this construction by Juels and Wattenberg is very, very simple. I have some input that is, I'm going to call this X, and I have some code book with some error correcting codes. I'm going to sample a random code from this code book. And I'm going to compute the offset of my input from this code. And this S is something called a public helper, right? This public helper is the only thing that I store on my device, and it's basically some random value, right? If my input is chosen as X and the C is random, then the offset is also random. So when I authenticate myself a subsequent time, let's say there's some small difference in the input, I'm going to call this X prime. Using this public helper, S, I'm going to compute the offset of X and S. And I'm going to get some new code word C prime. And it's the magic of these error correcting codes. If I choose my error correcting codes in a very strategic way, I can ensure that the C prime will decode to C. Okay. And I guess that's what error correcting codes do. They tolerate some small errors, right? So like you can imagine this as there's some like an epsilon ball around this error correcting code. Any code word C prime that falls within this epsilon ball, for example, will map back to the same code word. That's what this decode procedure does. And why is this code word important? This code word somehow is my secret, right? Cool. So this helper string, which is S, is basically some public information in the context of these fuzzy extractors. And these code words are the secret that help authenticate. The problem with these constructions from 1999 are they're limited to like basically binary inputs. So this X has to be like a binary string, which is really not representative of biometrics today. And these metrics, which is this dysfunction that you're seeing on the first bullet point, are limited to very simple metrics like the Hamming distance or set distance, which is also not representative of distance functions that are used for biometric embeddings today. Like we saw something with cosine similarity, for example, the earlier slide. So like, how do we actually solve this problem? Without going like too many details, we basically just use the same code offset approach, but we use, instead of standard error correcting codes, we use lattice-based error correcting codes. So lattices are some geometric construct which are used for designing new encryption schemes in cryptography. I'm sorry, I have a question on chat. Oh.
No, it's not really a question.
Oh, sorry.
So
okay.
Arnaldo says that he needs to leave. Yeah.
Right. Awesome. So we have like in the status quo, we have like this, let's say, Face ID, which has a deep neural network, and the output of Face ID is going to be some embedding. What I'm going to do with this particular embedding is I have like this code book of lattice codes. I'm going to pick a randomly chosen point from this lattice code book. I'm going to compute this offset like what we did in the earlier slide, and I have like some helper string. So it's subsequent authentication attempts, and this helper string is what I'm sharing as public information, right? So now I'm not storing my embedding anywhere. This lattice code book is also public information, so everybody knows about this. And the helper string is the only public information. So I'm doing away with the secure hardware altogether. So at subsequent authentication, I obtain some new embedding, right? Because I have glasses on, the embedding is different from the first case. I use this helper string to obtain some point in this lattice space. So if you look at the operations here, I'm performing some subtraction here to obtain the helper string. So obviously, if I perform addition, I'll get some point in this lattice space. And depending on how we choose this lattice, there's a technique called solving the closest vector problem, which is equivalent to my decode function. And if I solve CVP, I will get this original lattice point, assuming these inputs are at a bounded distance. Right, so that's a guarantee. And for those who don't know, like solving the closest vector problem in the lattice space is an NP-hard problem. So you can't do this for all lattices. You have to be very clever in how you choose your lattices, right? And these randomly chosen lattice points, I guess, are your secret somehow. So you can run a hash function on it or something, and you'll get some entropy. And your helper strings are public information as earlier. So, we have to cleverly choose the lattice, so on and so forth, do a bunch of things. And does this actually work in practice? Right, so we tried it on like a bunch of different data sets, and we measure like the false acceptance rate for authentication on the y-axis, and we measure compression on the x-axis. And we want to do compression because these biometric embeddings are very, very large, and running this computation with large embeddings is slow. So we want to compress the embedding as much as possible. So this side of the x-axis is more compressed embeddings, and this is like the full embedding. As you see that as you increase the compression, the performance actually becomes worse. You want a very low FAR. You want a very low false authentication, false acceptance rather, right? So for the original sized embeddings, you can see that the false acceptance is very, very low. I guess this number is kind of close to, yes, maybe this number is kind of close to what you get in the Face ID, for example, with secure hardware. And this is the numbers I guess you get without secure hardware. I mean, there is some performance penalty, but you're able to do away with some strong assumptions. So I guess the open questions here are, we're using deep neural networks to obtain these embeddings, but these deep neural networks themselves may be susceptible to like things like evasion, which might introduce collision. So how do you better design deep neural networks? Even for things like Face ID, we saw a lot of papers, I think they'll appear in Usenix this year, on how Apple proposed this technique to perform content moderation using fuzzy set intersection, but they're also susceptible to collisions. So anything that involves neural networks can be like messed with by people who know how to do evasion, right? These deep neural networks may kind of very strongly propagate bias and fairness issues. So how do we fix them? And like I said, we're using lattices, so this might be kind of slow, and you can't really do this for all lattices. But if you understand, the topology of the lattice space, you can design a more effective code book. So how do you understand this topology? That's an open question. Right, so let's quickly recap through what we discussed. The first thing we discussed how we can include some causal side channel information, which will improve the stability of generative models. And consequently, these generative models can be more utilitarian. In the next problem, we saw that if we look at membership inference through the lens of memorization, we can make the claim that samples that are highly likely to be memorized are also going to be very susceptible to membership inference. So we somehow understand when membership inference works better. In the third thing that we spoke about, we saw how you can use like construction of cryptography to give very strong proofs about operations that are being performed. So an alternative could be, one can perform unlearning and use techniques like backdooring. So for example, I can backdoor my data and request for it to be deleted. And at the later point, I can basically say, hey, the backdoor is present or absent. But like nobody really knows when that works and when it doesn't, right? Like so it's a very ad hoc solution. So these are not very reliable. And finally, you can use machine learning with cryptography to enable a new class of like private authentication mechanisms, like the ones with the fuzzy extractors that we saw. Right. So none of this would have actually been possible without like this list of like incredible collaborators that I've had like at multiple institutions around the world. Like very, very lucky to work with like these great set of people. I'm just going to use this opportunity to basically announce that our group at Microsoft is also looking for interns for the summer. So if any of you are interested, please reach out by email. I'm also looking to hire PhD students at Illinois. So if any of these topics seem interesting to you in any way, I'm happy to talk more. And with that, thanks for your time and thanks for listening. And I'm open to questions.